Hello, my name is Peter Lewin-Jones and welcome to my talk on the Introduction to the Finite Element Method. This is part of the Computational Toolkit seminar series in the HetSys CDT at the University of Warwick. I am a PhD student working in computational fluid dynamics, and the finite element method is the method that I use in my day-to-day research. So, quick introduction to what I'll be talking about. So in this talk, we'll be discussing the finite element method. I'm going to introduce the weak or variational form of a differential equation and what the Galerkin approximation is. And these are two key ideas to understanding how the finite element method works. I'll discuss finite element methods in one dimension, and we'll have a bit of a live demo. And I'll have a chat about how the finite element method works in higher dimensions. And I'll conclude with how the finite element method expands beyond the examples in this talk. Okay, so here's an example problem that we can solve using the finite element method. We have a second order differential equation here. Second derivative of u with respect to x is equal to some known function f of x on the domain 0, 1, where we're prescribing the values of our unknown u at the endpoints of the domain. This is what we call a boundary value problem because we have conditions on all the boundaries of the problem, unlike an initial value problem where all the conditions on the solution are specified at the start of a domain. This generalizes quite naturally into two dimensions, where we've got the Laplacian of our unknown u is equal to some known function f on some domain D, and we specify the value of the function u on the boundary of the domain D. And in particular, I'm not saying anything about the domain D other than that it is suitably nice. I'm going to be avoiding some mathematical technicalities in this talk, but in general, if I say something needs to be sufficiently nice, then there is some technical mathematical description of what I really mean by that, but I'm not going to go into that in this talk. If you want to study the finite element method mathematically, then there's lots of details that are important, but you can get a good understanding of the finite element method and how it's used practically without understanding all of these technicalities. Okay, so what do we mean by the weak version of a problem and the weak solution? Well, we start by integrating our differential equation after we've multiplied it by what we call a test function. A test function is any sufficiently nice, again, function, which is 0 on the boundary of the domain. If we now integrate by parts, we will now get a derivative of the test function appearing. We will lose one of the derivatives on u, and we'll use the condition that our test function is 0 on the boundary to remove these extra terms. And we have that now this integral is equal to 0 for this test function. So we can now write down the weak version of the problem. So we have this integral being 0, and this was for a general test function. And we'll note now that in the way we've integrated by parts, u and phi now only need first derivatives. And mathematically, this means that these are in a function space called a h1, 0, 1, 0, 1 here being our domain, and h1 being the type of function. This is a Sobolev space, but you don't need to understand these details again. Just want to show off that there is a lot of mathematical notation hiding away in here. The important thing for u and phi being in this space is that we need their first derivatives and they need to be integrable on this domain. And that's what them being in h1 actually means. We also specified that phi needs to be 0 on the boundary. And again, we'll use a subscript 0 on the space to specify that. So we can now write the weak form. So the problem that we're trying to solve is now find u weak in the Sobolev space h1, so that is find u weak that is integrable and has a first derivative with the specified conditions on the boundary. These are the same as from our strong form of this problem, such that for all test functions phi that are differentiable and 0 on the boundary, then this integral is equal to 0. So we've gone from wanting just to find a solution to a differential equation This is now a variational form in that we're saying that our solution UW needs to satisfy a condition for all of these test functions. Now, if we find a solution to this weak equation, call it a weak solution, this will also be a solution of the original strong problem. Again, assuming some technicalities. The function f needs to be sufficiently nice, the domain needs to be sufficiently nice. But these aren't particularly strong requirements, and anything that you'd reasonably come up with in a physical context will be nice. The reason this works is that this space of all possible test functions, and two test functions which are 0 on almost all of the domain, except for a very small piece. And so on that little piece, that'll fix the function to our function u to satisfy the original differential equation we had at the start. Imagine putting in a Dirac delta function as a test function phi. Dirac delta function isn't one of these equations in H01, but the idea is we can take a sequence of test functions that get close to a Dirac delta function. You would get back to the original set of the equation. But the main point is, although this is weaker in a sense, in that we're only requiring first derivatives on our weak solution, it will be a solution to the original problem. So the second part of this is called the Galerkin approximation. But before we get to that, we first need to deal with these boundary conditions that we're specifying the value, and in particular a non-zero value at the endpoints of our domain. So we split up the solution into a UP that satisfies these boundary conditions. So UP at 0 is equal to G0, UP at 1 is equal to G1. And then a second part, which is 0 on the boundary. So now our problem looks like this. Find UH in H01, so that is differentiable and integrable with 0 on the boundary, such that for all test functions in that space, this functional, which I'm going to call R, is equal to 0. And you can see all I've done is substitute UP in. But in particular, both our space of test functions and the space of our solutions are the same. So we're hunting for a solution UH in this space, and we're doing that by comparing against all of the functions in this space. So the next thing to do is expand into a basis of that function space and take both our solution as a sum, some coefficients times by that basis, and also our test function. We're also going to spot that this integral is linear in the test function. Now, well, it's also linear in the solution u, but if we had a non-linear differential equation, that wouldn't be true, but r would still be linear in the test function phi. And in particular, the fact that r is then 0 for all choices of phi means that when we've split it up into this basis, r must equal 0 for any choice of these coefficients phi j. So equivalently, our problem is find, that is a list of coefficients u in terms of this basis, such that for all of these basis functions, this rk is equal to 0. You can imagine, well, this has to be true for all test functions phi, but we can just take the subset of those test functions that are these psi j's. Plug that into R, and we'll find that this equivalent definition here. Now, the Galerkin approximation is to truncate this and just consider a finite subset of this basis. The idea is that you choose this sensibly so that this finite set of phi j basically capture all the information that you really need to know, and that the remaining infinite that you've got thrown away are actually providing only a very small piece of the solution. So as a quick aside, another version of this that you might well have seen are if you instead choose psi j to be sine functions. And suddenly, this is something that a lot of you will have heard of. The integration that we have is actually now a Fourier transform. So if I go back to here, this integration, if you imagine putting sine in here, just say for this f, f times by sine pi j x on this interval will actually be the Fourier transform of f, or a version of it given a Fourier transform given the conditions we've got on the boundaries that we put on this interval, and so on. Little detail is that the orthogonality condition on these functions means that this drk duj is a sparse matrix, which we'll talk about later why that's important, but it means that this is a very sensible choice of basis. And this works incredibly well in 1D or in rectangular 2D domains, because constructing a Fourier basis that is 0 on domain boundaries in rectangular domains is very easy. But you couldn't use these functions on a more complex domain, because your basis functions need to be 0 on a domain boundary, and trying to find that if the domain was much more complicated just wouldn't work. However, the finite element method does work on any domain, reasonable domain. And that's one of its key advantages, as we'll see later. So what is the finite element method? Well, unlike a Fourier basis, which they can use basis functions that are 0 on most of the domain, as I mentioned earlier. And what we're in fact going to use, we're going to use piecewise polynomials. So the domain is split into elements, each with a number of nodes, which are just points in our domain X. And then on each element, we have one test function per node, where that test function is 1 at its particular node and it's 0 at all the other nodes. And then these are joined together to create global test functions. But this is quite hard to imagine without drawings and pictures, so we're now going to do a MATLAB demo. There are quite a lot of different ways of structuring finite element code, and for this demo I've quite closely followed the algorithm described on the web pages of Oomph-lib, which is a package that I use for doing finite element simulations. We'll include the link to this guide in the description of this video. But it just means that my code is structured in the same way as this web page. So if you and I think it's quite a good way of understanding how this could. But however, there is a lot of technicalities of keeping track of different numberings of nodes, and so finite element code looks very long, but a large amount of it is bookkeeping of numbering of nodes within elements and with the whole domain. We'll see that in a second. Right. And yes, the example I'm going to be solving in this code is this. So I've just plugged in a particular function f, which is this minus 30 sine root 30x, and this has just been chosen because it looks nice and smooth to look at, and there's an exact solution that we can compare to. Oops, come back to that in a minute. Sneak peek of the 2D thing in a minute. Right, 1D demo first. So let's first of all look at a single element. So I've just set my code to have one element for now. I'm not pinning any of the domain boundaries, so I'm going to have the functions on this single element. And picking 2 nodes per element means I need 2 degrees of freedom on my polynomials per element. So these are going to be linear functions. So I run this, and these are my 2 basis functions. So we can see here, this is the second one. This is 0 at one node with a red X. It's 1 at the other node. And you can see we've just used a linear polynomial on this element. If I change to 3 nodes per element, you see we just flick through the examples, and here's the third element. This is 0 at this point, 0 at this point, and 1 at this point. So this is a quadratic, and we've needed a quadratic in order to get a polynomial that is 0 at 2 points and 1 at a third point. Okay, so just ready for when we actually solve it. So I'm going to pin domain boundaries, force our space to be 0 on the edge of the domain. I'm going to up the number of elements, go back to linear elements. I'm now going to plot the global basis functions that are actually used for solving this equation. So we can see here these are moving along, and you can see these are global basis functions phi, which are 1 at the particular node, and there's 0 everywhere else on the domain. It's a piecewise polynomial. So it's just a flat 0 everywhere, and then it goes up to 1 for its node and back down again. We can do the same thing with quadratic elements. Now you can see we have piecewise quadratic polynomials. So you can see sometimes it's on a single element, so it's smooth within the element and then it's zero everywhere else. Sometimes it's the basis function for a node that's on the boundary of two elements, like this last one, where when it's a boundary of two elements, it will pick up the polynomial from the two elements that neighbor that node. And so you'll see, but it'd be 1 at the top and then back down to 0 either side. So let's now actually solve an equation with this. I'm going to make it really low resolution so we can see what's going on. Just got some switches on my code here which turn on different parts of this code. So now 5 elements, linear functions, and then I'm actually going to solve it. And then we're going to see what the solution looks like. And I'm also going to plot the exact solution. Here we are. So the finite exact solution is this thin black line. Finite element solution is this dashed blue line. And I've just plotted the values of that we actually found for u at the nodes. You can see that those line up very nicely with the exact solution. And these aren't the thing. These aren't just, I haven't just drawn lines between the solutions on the node. The finite element method gives you a solution in terms of polynomials. So the solution includes the fact that these are linear between these nodes. To demonstrate that, if I switch to quadratic elements, still 5 elements, but now with 3 nodes per element. You can see that, in fact, I'll do it even less elements. Let's just put in 2 elements and see how good that looks. This is better. So now you can see I've only used 2 elements, but because there are 3 nodes per element, this first element goes from 0 to 0.5. But it's still using quadratics. So the fact that it's still curved in between these nodes is part of the finite element solution. And the fact that we have a polynomial basis means that this has actually tracked it better than a solution that was just computing purely at nodal values. And if I bump this up just a little bit, the solution gets very good indeed and tracks the exact solution almost exactly. The last thing to mention is that there's no need for the elements to be the same size. So I've also included something where I have split nodes between different parts of the domain. So here's an example where you can put more nodes at one part of the domain than another. I've just spread them so that there are more elements in the left part of the domain as opposed to the right. I think I put the divide at about 0.25. And this tracks together neatly. And so if you knew that your source function f, let's go back to that PowerPoint. If you knew that this source function f was, say, much sharper at one part of the domain than another, you might want to include more elements where you know that the function is changing more rapidly and you need more resolution. Okay, that's a bit of an overview of how it works in 1D. Well, what about in higher dimensions? So the great thing about the finite element method is that it works on any reasonable domain. So here I have just picked a sort of vague Pac-Man ghost shape, which I've just drawn up in 2D. So the first job in order to use the finite element method in multiple dimensions is you need to mesh the domain. So what does this look like? You divide up your domain into triangles. You can also do it with quadrilaterals, but for a domain like this, quadrangles make sense. We capture those arbitrary angles quite nicely, and this will also smooth out that circle that we had at the top of the domain. That comes out very nicely. And again, in 2D, we now have functions which are test functions, which are 1 at each of the nodes and 0 at all the other nodes. And again, we define them on each of these elements. So on a particular triangular elements that will contribute locally a shape function that looks like 1 at one corner and 0 at the other corners. And then for each node, we'll glue all the ones in the neighboring elements together and get a global shape function that's 1 at that particular node and 0 everywhere else. Then what we can do is do those integrals find the solution of where that big residual r was 0, and then get a solution that looks nicely like this. So here is where I've taken these Laplacian is equal to -3 as a source function. I've fixed u at the top, so I fixed it to 1 on that circle at the top of the domain. I fixed it to 0 on the little zigzag at the bottom of the domain. And then I used a Neumann condition on the right and left side of the domain, and I'll discuss how we implement that in a second. And then solved it. You can see that it comes out very nicely, and we've got a variable u, which I've just labeled by the color in the domain, that satisfies this equation with the required boundary conditions. And this works all very nicely, but this is a very complicated domain, and trying to do this with a finite difference method would be doable, but you have to be very careful about dealing with the domain properly, and in particular making your grid line up with a domain boundary like this is difficult, whereas in the finite element method, the mesh doesn't need to be in a regular pattern. We can just use some triangulation algorithm to mesh a domain and then compute a solution using the finite element method. So a few more properties. So boundary conditions on the derivative view, like I've used here on the sides, can be imposed by including the term that appears when you do integration by parts, and you let the test functions then not be non-zero on those boundaries. So if I rewind back to where I did that integration by parts, you can see here that here I've integrated by parts, and I would leave these terms in the residuals. If du dx was fixed to be 0 on the boundary, these terms would also disappear. But then the fact that these phi's are allowed to be non-zero on the boundaries would then also capture this condition. Or if du dx was fixed to some known but not 0 value, then I'd have an extra term in this integral that would also have to be 0. But that's straightforward to also include in the algorithm. That's where I was. Time dependence can also be included. So although I said it needed to be a boundary value problem, you could also have a time derivative, and you'd replace that time derivative with some implicit finite difference approximation. And you would then step forward in time. So at each time step, function would evolve, and then you'd solve for the spatial part using the finite element method. And it would just look like substituting in a finite difference approximation for a time derivative into the equations at each time step, where you've also then integrated and then got out the residual thing to solve for the finite element formulation. If you had a higher derivative in your differential equations, then you would need higher derivatives being possible on the polynomials, and so you'd need to use higher order polynomials. And it might be that different variables in your system, so if you had a multivariable system like we do in fluid dynamics of velocities and pressures, you might need different types of basis functions for different variables. I mean, even as trivially as if one variable was pinned to a particular value on the boundary, then the test functions for that would be 0 there. But if it had a derivative at that point for a different variable, then the test functions for that variable would be non-zero there. So you'd have a slightly different set of test functions in that case anyway. There's a lot of mathematical theory underpinning the finite element method, which I've touched on very briefly by mentioning Sobolev spaces, but there is a lot of theory explaining that why this works, why this gives you good solutions, why these solutions exist, whether they are unique, and in particular, how large the error is arising from the various steps of approximation that we've done. In particular, a lot of these error estimates are a priori, so you can say before you've done the computation how much error your solution is going to have compared with the exact solution. And this can be quantified in terms of the size of the elements used and also the order of the polynomials that you're using at each point. For linear problems, these RKs being equal to 0 is actually a linear system. You just have to do one matrix inversion. But for non-linear problems, this isn't. This is some non-linear vector equation you need to solve. You would solve this by using Newton's method. And in particular, specifying analytically what these derivatives of RK with respect to the unknown variables uj. You can give that Jacobian explicitly. That makes the solution much easier to compute, much more efficient to compute. And in particular, the fact that we've chosen basis functions that are zero most of the domain makes this Jacobian a sparse matrix, and you can use much more efficient algorithms for inverting it and for solving these linear systems in Newton's method. And this is also true of using Fourier basis. There, the Jacobian is also sparse, and that's why that method is so efficient. So, conclusion, finite element method is a numerical method used to solve differential equations with conditions on the boundary of a domain. It solves the weak form of the differential equations, and the solution computed is some piecewise polynomial function, where the domain has been split up into elements that you've meshed with some algorithm, and then you're going to get a solution that on each of that element, it's a little piece of polynomial, and they've been glued together to give you a global solution to the problem. It works really well with complicated domains, so where these have then been meshed with triangles or also with quadrilaterals are also used. I mean, much more complicated domains than even that little Pac-Man ghost. You could have holes in the domain. You can include part periodic domains, moving domains. That's what I use it for. When the domains are also evolving with the solution, it works well at as well. So the finite element method is used a lot in solid mechanics and in fluid mechanics. In solid mechanics, often the variables are the updated position of where a solid has moved to when some stress or some strain has been applied to that solid. Whereas in fluid mechanics, a lot of the time we're solving for velocities and for pressures, and these different problems could even be coupled together. So say a fluid that is pushing on an elastic solid, that would work very well with the finite element method, because you could use that to solve both the solid and the fluid dynamics part of the equation. So some major software that's actually used in practice, there are the big commercial packages. CompSol is the biggest one. There's also one called Abacus that is used a lot. And there are also some very good open source projects such as Finite and one called Free FEM. The one I use is a package called Oomph-lib, which is quite hands-on in terms of the mathematics being used, but is particularly good at these coupled multi-physics problems where, say, you've got a fluid and a solid interacting, or what I use it for is when I've got a fluid on a moving domain that is reacting to the fluid. And that's the end of my talk. I hope that's been a very brief introduction to how the finite element method actually works and what it looks like using it. It's a sort of method where you can use it for a differential equation that's already been specified quite easily. But if you want to solve a new problem, you have to get quite deep into the mathematics in order to write down the correct integrals in order to solve the weak forms of these problems. But it's a great method, in particular for complicated domains, and I would really recommend it. And it's worth looking into as an alternative method than, say, spectral methods or finite difference methods. And it works really well. Thank you very much.